So basically, if you look into these questions, basically you are using quadratic elements to approximate the temperature distribution. Basically, the temperatures of the nodal temperatures are already been given here. Right, it's already been given. So from node 1 to node 7, but then now you're asked to use a quadratic elements to approximate, okay, the temperature at x equal to 7 cm. Right. So if x equal to 7 cm, then it will be happen at, all right, at here, right? So it will be happen at here. So if using what we call quadratic element, then you need 3 nodes for one element. So that will be our this will be my element number 1, number 1, right? Number 2 and number 3. All right, so that is the shape functions are Si, Sk, and Sj. Okay, and you can refer to it. So what we are doing here is this is in local coordinates as shape functions. Right, so we need to determine our x and l basically. So if you are having the temperature at x equal to 7 cm, which is in global, then in local will be basically it happened at the element number 2. Okay, so we are saying that this T2 itself, and our x here will be our x here will be is here. So our x here is 2 plus 1 is 3. Okay, our sorry, is 3, and our L here is 4. Okay, 4 cm. Then basically we are having here is talking about the element number 2. So we have the S here is 3 T3 plus S4 T4 plus S5 T5. All right. So here we'll be having here is X. Anything? X over L minus 1 2x over L minus 1 D3 plus our S4 is 4x over L 1 minus x over L D4 plus here is x over L 2x over L minus 1 D5. Right, let's substitute everything in. I mean, we have the x is 3, which is in the element number 2. So we are focusing on here, right, element number 2, and the x is in local is 3, and the L is 4. Right, so here if we substitute everything in, then we have 3 over 4 minus 1 2 times 3 over 4 minus 1. Then our D3 is 56 degree. Then plus here we have 4, 3 over 4, 1 minus 3 over 4, multiply with 44, plus another one is 3 over 4, 2 times 3 over 4 minus 1. Right, then the D5 is 36. So it will give us our T is 39.5 degree. Right. So if you can use the linear elements to predict, then probably it will happen at, if I'm using linears, so that is the linear shape functions, right? So it happened at element. This will be, if linear, then let me use the other colors. So this is element number 1, element number 2, element number 3, element number 4, right? So if linear, then it will be T element number 4, S I T4 plus S J sorry, S4 T4 plus S5 T5, right? So here our X in this case is 1, our L is 2, right? Then we have 1 minus 1 over 2. T4 is 44 plus here we have 1 over 2. T5 is 36. So it gives us a 40 degree. Okay, so that is some 0.5 degree difference if we are using higher orders and quadratic elements. All right. 2 is more towards truss members, truss systems. Okay, you have a cross-sectional area of 2.3, and they are made of aluminum alloys. You are asked to use hand calculations to determine the deflection at joint, this particular joint A. When you have loads applied at 200 pound at this joint A itself. So we are also asked to find the stress as well as the reaction force. Right. So if you still remember, I mean, for truss system, we need to transform. So okay, because we have the orientation. So basically, that this thing is our K elements lah. Oh, so that this itself is our K elements. Okay, so here we have, if we assume this is our element 1, right? Element number 1, element number 2. Then we have this is my node 1, right? This is my node 1. This is I put this is my node 3. This is my node 2. So 1, 3, and 2, 3 in this case, right? So here my element number 1, right? Our T number 1, T. Sorry. Element 1, our theta equals to 60, right? Our element number 2, because I put this at node 2, this here is node 2, so basically is the theta is 120, right? So theta is 120. All right. So we can find the K, okay, for the what we call for each members is the same lah. Basically, this K itself is this K is A E over L, right? Before transformations, so we have the A 2.3, E is 10 times 10 to the power 6 divided by the length itself is 3 feet, is 3 times 12, 36 inch. So we have 638,889, right, pound per inch. So that is our K lah, basically. So to find our K1, okay, the first elements K1, then probably I'm applying this, okay, into with the theta of 60 degrees. Oh, so for K1 is 60 degree, for K2 is 120 degrees, right? So I have my K1 here is talking about multiply. I mean, you substitute with theta. Theta is 60 degrees. Okay, then multiply with the k here. Multiply with the k, which is 6388889 here. Then I have here is, or what we call, I can put k then 0.25, right? Point 0.433 is a 3 times 3, 4 times 4, negative 0.25, negative 0.433. Then I have 0.433, 0.75, negative 0.433, negative 0.75, negative 0.25, negative 0.433, 0.25, 0.433. Here is negative 0.433, negative 0.75, 0.433, 0.75. So here is actually referring to here, if we are looking, it is referring to U1x, U1y, U3x, U3y. Okay, so same with here, U1x, U1y, U3x, U3y. Right? So because it's not 1 and not 3. Okay, then for number 2 itself also the same number 2 k 2 with theta equals to 120 degree. This is theta equals to 60 degree for the element number 1. For element number 2, then we have our stiffness metric is 0.25, 433. Then we have 0.433. Then we have 0.433.75, 0.433 negative 0.75. Then 0.25 negative, 0.25 negative 0.433. 0.433 negative 0.75, negative 0.433, and 0.75. Again, here it is referring to U2x, U2y, U3x, U3y. Right? Right. So then we can assemble. Okay, we have the elements. Okay, we can assemble them before we apply the boundaries and also the loads. We can assemble them. Okay, so if you assemble, then from this is a 4 times 4 matrix, right? Because they are sharing the nodes 3, right? They are sharing the node 3. Okay, so these parts later on these parts will be sharing with these parts 0.25. All right, so that will become this is also 4 times 4. Then because they are sharing the same nodes, then our assembly global here K G will be a 6 times 6 matrix. All right, so here will be, if you refer back, I mean, here we have something to do with U, okay, sorry, U U1x, U1y, U2x, U2y, U3x, U3y. So same with here, U1x, U1y, U2x, U2y, U3x, U3. Right, so compare with what we have here, U1X, right, is 0.23, 433.73, right? So here will be a 0.25, right? Here we have the 0.25. I will put a K here, so our K global, of course, we have a K multiplied with this 0.25, 0.433, 0.433, and here is 0.75, right? This is from what we have here. Okay, so let me draw this. Right. Then 1, 3, okay. 1, 3 will be at here, this particular part, and this particular part will be at, will happen at here, okay. It will happen at here and here, and here and here. Right. So basically, from here, these two times 2 matrix we will be placed at here, negative 0.25, negative 0.433, negative 0.433, negative 0.75, right? Here is negative 0.25, negative 0.433, negative 0.433, negative 0.75, right? Then we have another part which is here, 3, which is the green one, 0.25, which is this one. I will draw it again. On note 3, we have this particular part. So we have 0.25, 433, 433.75, right? So it's at here, 0.25, 0.433, 0.433, 0.75, right? Then we have the second element, which is involving node 2 and node 3. So which is here, use another color. So here will be on node 2 itself. So 25, negative 0.433, negative 0.433.75 will be happen at here. Okay, node 2, 0.25, negative 0.433, negative 0.433.75. Right. Then we have also here 2, 3, right? And here is 2, 3. This particular two part will happen at here, here, and yeah, here, here. Okay, so these two is 4. So we have negative 0.25, 0.433, 0.433, negative 0.75, negative 0.25, 0.433, 0.433, negative 0.75. So the last part will be from here, okay, from this part, node 3. So we have 0.25. Right, then we have also minus 0.433, minus 0.433. Then we have also minus 0.433. Then we have 0.75, so it's plus 0.75. So basically, this gives us our global stiffness matrix. Right? Multiply with K, so our K, we have the values. Right, so with this, then we can apply our boundaries based on this itself. F equals to dk. This is our ku. So our F equals to ku, right? Then we can apply our boundary. So here is fixed. Node 1 and node 2 is fixed. So we have a u1x equals to u1y equals to u2x equals to u2y equals to 0, right? And our load applying, our F is actually applying at node 3, 3y, which is equals to negative 200 pound. Right, so the whole things, I mean, if you see that it will be further reduced towards only node 3. All right, so here we are talking about taking, maybe I will just cross it, right? So basically this part, this part, this part, right? So here also gone, gone, gone because of the boundary itself, right? So here we end up with only this. It's a 2 times 2 matrix. Okay, so here we have a 0.5, 0, 0, 1.5, right? And we have our u3x, u3y equals to our f. Our f is negative 200. Right, so solving this, we give us u3x actually equal to 0, and u3y actually equals to a negative 2.087 times 10 power negative 4. Okay. So that gives us the displacement, or what we call the its deflections at joint A itself. Okay, it's purely verticals. So continue to that, we need to determine the stress. Why? Okay, we need to determine the stress also, and the reaction force, right? So of course you can use first, I mean, because talking about stress, then you have to from our so-called global coordinates, okay, global deflections, deflection in global, okay, then you have to transform back to locals, so local at around this along the member itself, then we can find the stress. So what you can do is either we use we have the global already, right? So now if we find the inverse transformation matrix multiplied with our global deformations, then basically it gives us our local deformations, right? So where our T inverse equals to T transpose equals to cos theta sine theta negative sine theta cos theta 0, 0, 0, 0. Then we have right. So you can use this, right? But then because this is a simple two models, two members, or two elements, so probably if you look into this particular member itself, this is 60 degrees, this is our node 1, this is our node 3, right? So we have a u3y, which is equals to 0, sorry, here is about negative, okay, 2.087 times 10 power negative 4, right? So here will be 30 degree, and here is our y and x. So if we can find its if we can find its u3 x in this case at this particular point itself, then probably we can find the stress. All right. So what we need to do, if you look into this, this is 3y, right? So if looking into this member, if I want to find the stress, basically is E our strain itself, right? Is E. Here is talking about U3x. Okay, is in local U1x. Okay, divide by the L itself. Okay, so we need to find the U3x and U1x, and we know that this U1x is 0. Okay, along that particular this member itself at node 1. Okay, this is node 1. So we need to find the U3x in local coordinate. So what we need to do is basically we transform with the U3x. So our U3x here is U3x here is actually equals to negative, right? Negative 2.087 times 10 power of negative 4 cos 30 degree. Oh. So it's actually give us negative 1.8074 times 10 power of 4 inch. Right? So if we have this U3x, okay, basically is based on the U3y is going down, right? We are getting here, okay? We are getting this information, right? Then we have our stress in this case is E negative 1.8074 times 10 power negative 4 minus 0 divided by our L here is 3 times 12. Okay, so it will give us close to negative 50 times 21. Okay, pound per inch square. So it's compressions lah. So for element number 2, this is on element number 1 or member number 1. For member number 2, here will be given the same E will be U3x minus U2x, right? Divided by L. Against our U3x is the same. So it will also give us E negative 1.8074 times 10 power negative 4 minus 0 divided by 36 also equals to negative 50.21 power per inch square. All right, so that gives us the stress of each member, which is the same, which is negative 50.21 psi. Right. Then to calculate the reaction force, right? We of course we can make use of, if you have the total this U itself. Okay, we have this U already. We have everything. Then we can actually find the reaction force. If you still remember, basically is K G U. Okay, minus F. Sorry. So F, you can do that. So to find the entire reaction force of probably here is related to R, you will get this, our R itself will be 6 times 1 matrix. We have this R X, okay, or R1X, R1Y, R2X, R2Y, R3X, R3Y. Okay. So, or in the local forms, okay, if you are in local coordinates, then probably we can also find our R itself is F, okay, 1 with the force itself, talking about this particular point, F1 equals to our K U 1x minus U3x. right? So here we are having our, if you are looking into this particular plane itself, if you are looking into this particular point itself, the F1 here is like what I mentioned to you, K U1x minus U3x. Right, so we have our F1. Right, if we have our F1, then it will be equals to 6388890 minus negative 1.8074 times 10 power negative 4. So it gives us 115.5 pound lah, okay, in this case. Right, so this is in the local direction, local coordinate direction, this force. So we if this is F1, so if we can decompose it into our y and x directions with the 60-degree, then we will also get our R1 x will be equals to 115.6 cos 60-degree will be equals to 57.73 pound. R1y here will be 115.6 sine 60-degree will be 100 pound. All right, so that is its reaction force for node 1, and node 2 also the same same things lah. Basically, we are talking about node 2. You have to find our F2 here. It will give you K U2x minus U3x. So you will also get the same results. Then from this, you have R2x equals to 115.5. All right. Here is going the other sides. So you have this negative at here, cos 60. So we have negative 57.73. R2y also is 115.5 cos sine 60. So it's 100 pound. Right, it's going up. This is going this way. It's going this way and this way. All right, so that will be a question that related to truss systems. Next is on axial members. So axial member will be quite straightforward. So if you have these axial members and it is fixed at two ends here, right? Then determine the deflection at point D at here and as well at point F, right? Yeah, asked to find here and here. So what we can do here, first we have to find the we can split into two elements. So here we have our element number 1, element number 2. Okay, so then we have a 3 nodes here. So this is my node 1, node 2, node 3. Right, so later on to get of course we can put more nodes. We can put more nodes that including node D and node F, then whatever that we have solved, basically the nodal the deflection will be reflecting in the solutions. So else we can use the like what we are familiar with, lower elements, number of elements or lesser nodes. Then later on we use shape functions to determine the linear shape functions or even quadratic shape functions to determine the deflections or deformation at the requested point D and point F. All right, so again this is K. We know that is under axial is AE over L, right? So we have first K1 elements. We have A will be 1, right? 1. Then E will be given 29 times 10 power 6. Okay, divided by the L is 10 inch. Okay, then we have 1, negative 1, negative 1, 1. All right, so it's actually equals to 229 50. Right, so that is our K1. So for K2, K element number 2 here will be the A will be slightly smaller, 0.5. E will be the same, 10 power 6. Divided by the length here is also the same, 10 inch. Okay. So it will give us 145. All right. So this is 2 times 2. This is 2 times 2. This is 2 times 2. So sharing the node number 2, right? So then we have a K global will be K global will be a 3 times 3 matrix. Right. So will be 290 negative 29. So we have this 29 0 0 plus 145 negative 145. Right, so that gives us our global slew matrix. Then we can apply our boundary. So here, of course, our displacements, I mean, talking about 3 times 3, then we have our K U equals to F, right? So this is 3 times 3, 3 times 1, 3 times 1. So our U itself, right, is U1, U2, U3, right? So boundary, apply boundary. We have U1 equals to U3 equal to 0, right? So that whole things basically become if you have this, then basically it will become U2. Okay, so you have where should I write? Wanna so end ups where you have basically these parts. We have our K. Right. I don't need to write all of her here. So we have basically here our F will be also 0 5,000 0, right? So here, if we can after we apply the boundary, then probably this particular row gone, this particular number 3 also gone. So we are having this U2 2900 plus 14500. Okay, U2 equals to F2 equals to 5000. So it will give you U2 equals to 0.00114943 inch. All right. So to find, then we have our U1, U2, and U3, right? So we have U equals to 0, right? Then we have a 0.00144943 and 0 inch. Then we can find our so-called deflections at point D, which is using the shape functions. So here, if we are using point D at point D itself, our X will be 5, our L will be 10 inch, right? So it will be happen at element number 1. So U1 will be S1 U1 plus S2 U2. So here U1 will be 0, right? So we have S2, which is the equals to X over L U2 equals to 5 over 10 multiplied by 0.00114943. It will equal to 0.000574,715. Right, so at point F, also the same, our X equals to 5. If using local, then our L equals to 10. Then U at element number 2 will be S1, S2 U2 plus S3 U3. Right. So here U3 is 0, so this thing is gone. Then our S2 will be 1 minus X over L U2. So we have 1 minus 5 over 10, right? Multiply with 0.00114943. So will give us the same, result. 0.000, right? 574715 inch. All right. Then looking to we need to find the axial stress, right? If you are asked to find the axial stress, then will be stress at element number 1 will be E U2 minus U1 over L, right? So we're having E is 29 times 10 power 6, U2 is 0.00114943 minus 0, right? Over L here is 10 inch. Then it gives us the stress will be 3333.35. Okay. Element number 2, stress will be E U3 minus U2 over L. Right, then we have 29 times 10 power 6, 0 minus 0.0011493 divided by 10. Right, so here is a negative 3333.35. Right, so this is under compressions, right, when it is being going in here. So member number 2, this is going compressions. Then of course B is under tensions, positive. Right. So that gives us the information of stress. Next will be on beam. So probably need to show you here. So if I have a wide flange W16 times 31 with a cross section of this 9.12, the depth itself is 15.88. Second moment, the I itself is 375. Then the beam is subject to a uniformly distributed loads. Here is 1,000 pound per feet. At a and a point load, we have two type of loads here. That's why I'm putting later on our matrix. Okay, load matrix, we're having the distributed loads at the first element, the point load at the second element. Okay, so the modulus of elasticity E is 29 times 10 power 6. Then using manual calculations, okay, determine the vertical displacement at node 3 and rotation at node 2 and node 3. All right, so here this is fixed. Okay, so you if you are putting in two elements, so this element number 1, this is element number 2, right? So I have node 1, node 2, and node 3, two elements, 3 nodes. Then I have each of them. Here is U. Here we are talking about one. So we have this U 11 U 12 is equals to 0, right? So here the deflections here is also U21 is also 0, U22 is non-zero. Okay, its rotation is non-zero. U31 and U32, okay, is also non-zero. So in this case, probably we can find making use of what we have derived previously, the elemental stiffness matrix for a beam itself is as you see here. Okay, then the load matrix for distributed load will be as you seen here. Okay, that will be our load matrix will be here is negative WL over 2, negative WL square over 12, negative WL over 2, WL square over 12, right? So for this particular case, that will be our first elements. This will be our second element. Load matrix will be P over negative P over 2, negative PL over 8, negative P over 2, and PL over 8. Right, so that is our first so-called and second elements load matrix. So for our first stiffness matrix here, of course, you can use this, okay, stiffness elemental stiffness matrix in general, but then our E will be the same, okay, because the same materials. I will be the same because it's the same beams. Then the L will be different. So from 10 feet, okay, elements, this element L will be replaced by 10 times 36. 10 times 12, sorry, is 30, 120, sorry. 10 times 12. Then for our K, element number 2, we have our L is actually equals to 5 only. So here we'll be talking about 5 times 12. Okay, so that basically give an idea of what we would have. Okay, so we have a K1, K2, F1, F2, then we can actually assemble them to give us our so-called K at the end, okay, U equals to F. So here we have 3 nodes, right? So this will be, of course, 3 nodes times 2. One node got 2 degree, so we have a 6 times 1 matrix here. So of course here our K will be a 6 times 6 matrix, then this is 6 times 1 matrix. So when we assemble that. So to determine our K1 and K2, basically we are using the substitution of these the formulas that you see here. We have our K1, then basically we substitute with 29 times 10 power of 6. Our I is 375, right? Our L for number 1 is 10 times 12, right? Multiply with 12, 6, 120, negative 12, 6, 120, 6, 120, 4, 120 square, negative 6, 120, and 2, 120 square, negative 12, negative 6, 120, 12, negative 6, 120, 6, 120, 2, 120 square, negative 6, 120, and 4, 120 square. Right, so it will give us our the first stiffness matrix will be yeah, I'm just writing here, so you can cross check with yours 4, 5. Right, 36250. Maybe 45 31250 18125. Then we have 7 negative 75521, negative 453150, 75521. We have negative 453150, 453150, 18125. 453150, and finally we have 23625. Right, so that will be the first stiffness matrix. The second stiffness matrix for second elements here is the shortest length. Here is referring to 5 feet. Okay, 5 times 12 is 60. Right, so here will be 29 times 10 power 6, 375. Then we have this 5 times 12, 60. Okay, so we have 12, 6 times 60, negative 12, 6 times 60, 6 times 60, 4 times 60 square, negative 6, 60 to 60 square, negative 12, negative 6, 60, 12, negative 6, 60, 6, 60, 2, 60 square, negative 6, 60, 4, 60 square, right? So it will give us the 4 times 4 matrix here. Just write it out so you can later on cross check. 18125. 725, 3625. Right, negative 604167, 4167, negative 1812500. Then we have 1812500, 3625, Then we have negative 1, 1, 2, 5, 0, 0, 0, 7, 2, 5. Right. That gives us the second Stephen matrix, right? And just now we have also our load matrix here. We have determined our load matrix. Let me just finalize it. Okay, F1 here is equals to negative 1,000, right? Pound per feet, right? So, and it's over 10 feet, WL. Then divide by 2. Then we have negative 1,000 times 10 square times 12 divide by 12. Then we have negative 1,000 and 10 divided by 2. And we have 1,000 10 square times 12 divided by 12. So this will be our first different matrix. Then multiply, our second load matrix. Just now is the first load matrix, first element of load matrix. Second one will be negative 500 divided by 2, negative 500 times 5 times 12 divided by 8, negative 500 divided by 2, and also 500 times 5 times 12 divided by 8. All right. So it gives us is negative 5,000 pound, negative 100,000 pound each, negative 5,000, negative 100, sorry, positive 100. So here will be negative 250, negative 3750, negative 250, 3750 pound inch. Right, so that gives us the entire so-called all the elemental Stephen matrix and also the load matrix. All right, so here, if I can draw it out, I can write it out, is our K global, then we have this U global equals to our F, right? So our U here is referring to U11, U12, U21, U22, U31, U32. All right, so that is equal our F. Then basically we add them all these numbers up lah. So from what we have just now, you just fill in. Okay, 75521. Here is 4531250, 4531250, negative 75521. Then we have a 4531250. Then here will be we have here will be a 00 here, right? Then we have here will be 3625, negative 4531250. Then we have 18125. Right, so here will be 00. Then we have a negative 75521. 4, 5, 3, 1, 2, 5, 0, 7, 5, 5, 2, 1. I will write. That will be a sharing, I mean, of node 2. Okay, so let me put it up a bit. 5, 5, 2, 1. Then I have negative 4, 5, 3, 1, 2, 5, 0. Then I have this 4, 5, 3, 1, 2, 5, 0, 1, 8, 1, 2, 5. Then I have here will be against we have a sharing negative 4, 3, 4, 5, 3, 1, 2, 5, 0. And also here is a 3, 6, 2, 5, 0. All right, so here will be 0, 0, 0, 0. So that gives us the first we fill in the first stiffness matrix, right? A 4 times 4 matrix. Then the next is the second elements. We have here is sorry. We have here is a 604,167. 604,167. We have sorry, here 6, it's not here, so here 604,167 1812500 1812500. Right, so then we have also the second one is 18125000725. That will be a large one. Right, then negative 18125003625. Then just complete the entire stiffness matrix. So I have negative 604,167 1812500. Then I have here is negative 1812500604167 negative 1812500. All right, so that completes the entire global stiffness matrix. Then the load matrix, of course, we have the 5,000, 100,000, negative 5, 5,000 plus negative minus 250 is negative 525. I will write both together. Sorry, negative 5,000 minus 250, negative 100,000 minus 3. Sorry, this is positive. Positive 37 minus 3750. Then we have negative 2503750. All right, so again, if just now, okay, if you clearer, okay, on the boundary, right, actually we do not really need to compile the entire stiffness matrix. So if you are looking into applying if you apply boundary conditions, basically it actually we know that, as I mentioned to you, u11 equals to u12 equal to 0, u21 also equals to 0, right? So the first 3 row and the column actually can be ignored in this case, right? So talking about these right? So actually you do not really need to write this. So we end up having this is a plus, okay? So we end up having just 3 times 3 matrix lah. So here, if you can look into it, we are getting these 4 solutions. Okay, so it will give you U31 equals to, sorry, U22. It will give us, if you send for solutions, U22 equals to 2.3448 times 10 power negative 4 radians, right? And U31 equals to U31 equals to 0.013034 inch. U32 equals to 2.1379 times 10 power 4 radian. Okay, so that gives us our final results. So if you want to compute the reaction force, of course, like what we have mentioned just now, right? You have to use reaction force equals to K global, okay? You have to be K global multiplied with U minus F global, right? So we are talking about this is a 6 times 1 matrix. Then we are talking about this 6 times 6 matrix. Then 6 times 1, 6 times 1. For your informations, if you have got your R1s, okay, later on you will be getting R1 equals to, you've used this R, okay, multiplied with K global multiplied with U equal minus F, okay, global 6 times 1, 6 times 6, 6 times 1, 6 times 1. You have your R1 equal to 6062 pound, R2 M1 equals to 142494 pound inch, R2 equals to 4438 pound. All right, so that gives us our final result.